Welcome, curious minds, to another deep dive. Today, we're embarking on really a fascinating journey. We're looking into a foundational process, one that has quite literally shaped the modern world.
That's right.
We're talking about manual metal arc welding. You might know it as shielded metal arc welding, or maybe just MMA or SMAW. Think of it like a masterclass in controlling molten metal. It's this blend of, raw power and incredible precision.
It really is.
We've gathered a whole stack of insights today. We'll explore its really intriguing history, the intricate mechanics of how it actually works, the essential gear you need.
Yeah, the basics.
And all those critical variables, the things that separate a good weld from, a truly great one.
Indeed. And our mission today really is to peel back those layers. We want to reveal the core principles, understand why this process has stuck around for, over a century now?
Amazing, isn't it?
It is. We'll delve into the absolutely crucial role of human technique. Yeah. Why, even with all our advanced technology, this method is still so vital and, frankly, so challenging. Get ready to understand not just the what, but the deeper why behind this surprisingly artistic industrial process.
Yeah, prepare for some genuine aha moments, because this deep dive, it's packed with surprising facts and practical insights. I think you'll get a whole new appreciation for the sparks that fly. Okay, so let's kick things off right at the very beginning.
Good place to start.
It's truly remarkable when you think about it. MMA welding, it first sparked into existence way back in 1888 in Russia.
Yeah, 1888.
And when it started, it was incredibly basic, just a bare metal rod. Can you even imagine the limitations that must have imposed?
Oh, absolutely. That's a really critical point to grasp. Those early bare metal electrodes, they created welds that were frankly brittle and full of impurities.
Because of the air getting in.
Exactly. The molten metal was completely exposed to the atmosphere. So oxygen, nitrogen, they just readily combine with that hot metal. You'd get oxides, nitrides.
Stuff you don't want.
Stuff you definitely don't want. It severely weakened the weld. The joints were often weak, prone to failure. It really limited where you could even use this new technology.
Right.
It wasn't until the early 1900s that the real breakthroughs started happening. You had innovations like the Kahlberg process in Sweden and the quasi-arc method in the UK. These introduced those crucial coated electrodes.
The game changer.
Like absolute game changers. They essentially created this protective bubble around the weld. And that dramatically improved its strength, its ductility.
Yeah.
Huge step forward.
And it's amazing because even with all the really sophisticated welding tech we have now, MMA is still just incredibly versatile, isn't it?
It really is.
Suitable for most ferrous, non-ferrous metals, tackles a wide range of thicknesses, and crucially, you can use it in literally all positions: flat, horizontal, vertical, even overhead.
That all-position capability is huge.
Plus, it's relatively economical to get set up. That's quite a resume for something that old.
It is, and what's truly fascinating is that despite its age, its enduring popularity comes precisely from those practical advantages. Yeah. It's the absolute go-to choice for maintenance, for repair work, field fabrication, places where portability and that all-positional capability are just paramount.
Makes sense.
But, and this is a key takeaway, something we'll keep coming back to, the final weld quality, unlike maybe some automated processes, it's overwhelmingly dependent on the skill. The dexterity of the welder.
That human touch.
That human touch is absolutely everything here.
So, okay, how does this incredible process actually work then? We know the welder strikes an arc, right? Between the coated electrode and the workpiece. And this instantly creates this intensely hot, really localized heat source. It melts both surfaces, forms what's called the molten weld pool.
That's the heart of it.
And get this, the average temperature of that arc is a blistering 6,000 degrees Celsius.
6,000. Yeah, it's incredibly hot.
Hot enough to melt the parent metal, the core wire of the electrode, and its flux coating, all at the same time.
Which immediately brings up the critical question. What's protecting that super hot molten metal from the air around it?
Right, because air would ruin it.
Exactly. And this is where that flux coating really earns its stripes. As the electrode burns, the flux decomposes, right?
Yeah.
And it does two key protective things.
Okay, what are they?
First, it generates this shield of inert gas. Think of it like a localized protective bubble. It physically pushes the atmospheric oxygen and nitrogen away from the weld pool.
Okay, displacement.
Precisely. Second, it creates a layer of molten slag. This floats on top of the weld pool.
Like a liquid blanket.
Kind of, yeah. It provides a second physical barrier against contamination, but it also does more. It helps shape the weld bead and control how quickly it cools down.
Ah, interesting. And once the weld is done and the metal starts to cool, that slag solidifies, right, into a crust.
That's right. It forms a solid crust.
And that has to be chipped off the weld bead carefully.
Yep. Manual removal.
Yeah.
Shipping hammer time.
So that manual step, plus the fact that each electrode only lasts so long.
Right. They're finite.
It means welders are constantly stopping, starting, putting in a new electrode. It's part of the unique rhythm of the process, isn't it?
It absolutely is. Leads to those shorter, segmented weld lengths. And that aspect alone really contributes to its, let's say, distinct productivity characteristics compared to other methods.
We'll definitely circle back to that productivity point. So, okay, if you're looking to get into MMA welding, or maybe you're just curious about what's involved, what's the essential toolkit?
Good question. The good news is the basic equipment is surprisingly straightforward. Robust, too.
That's one of its appeals, right? Simplicity.
Absolutely. At its core, you need a constant current power source. Now, this can range quite a bit. You've got older, heavy transformer rectifier units.
The big boxes.
The big boxes, yeah.
Right.
Still workhorses in many shops. Or you could have robust generators for site work, where there's no grid power.
Right, for field work.
But increasingly, we're seeing these compact inverter power sources. They're incredibly portable, offer really precise control. They're kind of transforming where and how MMA welding can be done.
Lighter. Easier to move around.
Much lighter. Beyond the power source, you need an electrode holder, sometimes called a stinger.
Stinger, okay.
That clamps onto the electrode. You need the right power and power return cables to complete the circuit. And critically, absolutely non-negotiable for safety.
The visor.
The welding visor, yeah. With the correct shade rating to protect against that intense UV light and heat, modern control panels on the power source let you tweak things like amperage, polarity, giving the welder really fine-grained control.
Let's talk about that power, actually, because it's not just on or off. MMA welding can use either direct current, DC, or alternating current, AC. And that choice, it's not just a technical detail, is it? It fundamentally impacts the weld itself. Can you maybe illuminate what that means for the welder and the material?
Absolutely. It's a fundamental choice. With DC, the current flows in one consistent direction. This gives the welder these powerful polarity options. DCEP, that's direct current electrode positive, and DCEN, direct current electrode negative. And the fascinating part here is that which polarity you choose dramatically dictates where the intense heat of the arc gets concentrated. It's a key factor in controlling penetration and how much metal you deposit.
Okay, this is where it gets really interesting for control. Let's take DCEP first. Electrode positive, workpiece negative. Electrons flow from the workpiece to the electrode.
Correct. Negative to positive.
So what does that do to the heat distribution? You said about 2/3 of the heat ends up at the electrode tip.
That's right. Roughly 2/3 concentrates right there at the electrode tip.
And the practical upshot of that for a welder, what does that mean?
Well, the main implication of DCEP is increased weld penetration. Because so much heat is at the electrode, it actually burns off a bit more slowly, allowing the arc energy to dig deeper into the base material.
Deeper digging.
Exactly. So this makes DCEP ideal for welding thicker materials, or maybe for root passes where you absolutely need that deep penetration to get full fusion right at the joint, or for using certain specialized electrodes, like low hydrogen ones.
Got it. Okay, conversely then, DCEN. Polarity flipped. Electrode is negative, workpiece is positive. Now electrons flow from the electrode to the workpiece.
Right, the flow reverses.
So what happens to the heat distribution now? And why would a welder choose this setup?
With DCEN, the heat distribution flips too. Now, approximately 2/3 of that arc energy is generated in the parent material itself, in the workpiece.
Okay, heat in the workpiece.
Which means the electrode melts much faster. It has a higher deposition rate. But because the main heat is in the workpiece and the electrode's melting quickly, it actually decreases the depth of penetration.
Less digging, faster filling.
Pretty much. So this makes DCEN excellent for welding thinner materials where you really want to avoid burning through. Or maybe for building up materials, surface layers, where you want deposition without deep melting. It gives the welder really precise control over how much the base metal gets affected.
It really highlights the level of control just flipping a switch gives them.
It's fundamental control, yeah.
And then there's the third option, AC, alternating current. where the current just flips back and forth really rapidly, said 100 to 120 times a second.
That's typical, yeah. Constantly reversing direction.
So what's the outcome of that constant switching for the weld?
Well, with AC, because the current is always switching, you get an essentially equal distribution of heat. Think of it as a 50-50 split between the electrode and the workpiece.
Balanced.
A balanced penetration and deposition profile. But AC also has another distinct advantage. It helps to mitigate something called arc blow.
Arc blow. What's that?
It's basically a magnetic deflection of the arc. It can happen with DC welding, especially in tight corners or near edges or around magnetic materials. The magnetic fields can literally push or pull the arc sideways.
Making it hard to control.
Very hard. It can make the weld pool erratic, difficult to manage. AC's alternating nature effectively cancels out these steady magnetic forces, leading to a much smoother, more stable arc, especially in those tricky situations.
Okay, that makes sense. Now, beyond the type of current, the power source itself has to deliver specific electrical characteristics, right, to make MMA viable.
Absolutely. It's not just about having power, it's about the right kind of power.
It needs an open circuit voltage, OCV, you said 50 to 90 volts, just to get the arc started.
Exactly. That initial voltage jump is needed to bridge the air gap and initiate the plasma arc.
Then, once it's running, it needs to maintain a stable welding voltage, much lower, like 20 to 40 volt.
Correct. That's the voltage needed to sustain the arc while welding is in progress.
And it needs a suitable current range. You mentioned maybe 30 up to 350 amps, depending on the job.
Yeah, a wide range to accommodate different electrode sizes, material thicknesses, joint types. Flexibility is key.
And crucially, it has to deliver a stable, constant current. We saw a diagram showing this as a drooping output characteristic. Why is that droop so important for the welder?
The drooping characteristic. It isn't just a technical spec, it's really the hidden hero of MMA welding stability.
How so?
Think about it. A welder's hand, it isn't perfectly robot steady, right? As they weld, the arc length, that distance between the electrode tip and the workpiece, it's constantly fluctuating, just a tiny bit.
Micro adjustments.
Exactly. Now, if the power source didn't have this drooping output, meaning if the current stayed high, even when the voltage briefly increased as the arc lengthened, those tiny changes in arc length would cause huge, wild swings in the welding amperage.
Making it unstable.
Completely unstable. It would make it virtually impossible to maintain a steady arc, a consistent heat input, and therefore a uniform weld bead. This drooping characteristic means a small change in arc voltage, due to arc length changes, results in only a small change in current.
It smooths things out.
It inherently stabilizes the process. It basically forgives those minor inconsistencies in the welder's hand movement, letting them focus on guiding the molten pool and making the weld. Without it, MMA welding would be far, far too erratic and difficult to control reliably.
Gotcha. Okay, so beyond the power source intricacies and the setup, we get to the welder themselves, their technique, their mastery of certain variables. That seems paramount.
Absolutely paramount. The machine provides the potential, the welder provides the execution.
We identified 3 really crucial factors they control that directly impact weld quality: current, or amperage, voltage related to arc length, and travel speed.
Those are the big 3. The levers the welder is constantly adjusting, feeling, responding to.
Let's break them down. Understanding how they interplay seems key to the whole artistry of it. So first, current or amperage.
Right, amperage. This is essentially the rate of electron flow measured in amps. It directly controls how fast the electrode burns off and, critically, the depth of penetration into the parent material.
Okay, so what happens if it's not set right? Let's say too low.
If the amperage is too low, you'll see immediate problems. Poor fusion is a big one. The weld just won't melt properly into the base metal. You get lack of penetration. The weld bead itself might look irregular, maybe lumpy.
Cold looking?
Yeah, kind of cold. And you'll likely get slide inclusions trapped in there because the weld pool isn't hot or fluid enough to float that slag out effectively. The arc itself will feel unstable, maybe sputtering instead of that smooth hiss, and you can even get porosity.
Okay, not good. What about the other extreme, amperage too high?
Too high brings a different set of problems. You risk excessive penetration, maybe even burning right through thinner materials. You'll almost certainly get severe undercut.
That groove along the edge.
That groove, exactly, which weakens the joint significantly. You'll see excessive spatter, those little molten metal balls flying everywhere, which is messy and wastes electrode material. Porosity can also be an issue with too high amps, often due to the violent arc action. You might get deep craters when you stop the weld. And just overall, really high amperage makes positional welding incredibly difficult because the weld pool becomes too large and too fluid to control against gravity.
Right, it just wants to run away.
Okay,
second variable, voltage. You said this is linked to arc length, which the welder controls.
Correct. The power source sets a potential voltage range, but the welder actively controls the actual arc voltage by maintaining the arc length. That gap between the electrode tip and the workpiece typically operates between 20 and 40 volts.
And this voltage influences the weld pool's fluidity and the arc shape.
Profoundly. It affects how wide the arc cone is and how fluid the molten metal becomes.
So what if the voltage is too low, meaning the arc length is too short?
If the voltage is too low, arc too short, you'll struggle. Again, poor penetration. But you also risk the electrode stubbing, literally sticking directly into the weld pool.
Shorting out.
Yeah, causing repeated short circuits instead of maintaining a stable arc. This leads to lack of fusion defects, where things just aren't bonding properly. You might get accidental arc strikes on the base metal outside the joint, which are stress risers. And the arc itself just feels tight, constricted, unstable.
If it's too high, arc length too long.
Too high, arc too long. You're looking at excessive spatter again, a sign of an unstable, maybe wild arc. Porosity can crop up. The arc might seem to wander erratically instead of being focused.
Hard to aim.
Exactly. The weld bead shapes tend to become irregular, often too wide and flat, and the weld pool gets very fluid, almost watery, which makes any kind of positional welding, vertical, overhead, extremely tricky because the molten metal just wants to sag or drip away.
Okay, makes sense. And the third key variable, travel speed.
Right. Simply how fast the welder moves the electrode along the joint. This directly affects the heat input per unit length of weld, and consequently the shape and size of the weld bead.
So what if you go too fast?
If the travel speed is too fast, you don't put enough heat in. The weld bead will be narrow, often convex or humped up, and thin. It cools too quickly.
Trapping things.
Exactly. Rapid cooling can trap slag inclusions. It often leads to poor fusion along the edges, and you'll frequently see undercut because the arc is moving too quickly to properly fill the groove it's melting.
And the opposite, too slow.
If it's too slow, you put too much heat in one spot. You risk cold lap or overlap, where the weld metal just piles up on the surface without properly fusing into the base material below or at the edges.
Just sitting on top.
Just sitting there. You get excessive weld deposition, basically wasting material by putting down too much metal. This creates an irregular, overly bulky bead shape. And ironically, you can still get undercut sometimes if the heat dwells too long and melts the edges away without enough filler metal flowing in.
Wow. So putting it all together, what does this mean for the welder on a practical level?
It means the balance of these three: current, voltage, arc length, and travel speed is incredibly delicate. It's dynamic.
Not just setting dials and going.
Not at all. It's not just knowing the textbook numbers. It's about developing this almost intuitive feel for the molten metal. You're constantly making micro adjustments to the arc length to match the electrode's burn-off rate. You're listening to the sound of the arc. A steady crackle or hiss is usually good. You're watching the weld pool, seeing how it flows, how the slag behaves, how it solidifies just behind the arc, all to create a weld that is structurally sound, free of defects, and has the right shape and size. It really, truly underscores why welder skill is so critical. It elevates it beyond just a mechanical task. It's a highly nuanced craft.
A craft, yeah. That seems like the right word. Okay, so like any process, MMA welding, it has its distinct pros and cons. Our analysis kind of laid out why it persists, even with all the newer options.
It did. On the advantage side, it's just exceptionally adaptable. It's equally at home in a nice, controlled fabrication shop.
Or out in the mud.
Or out in the mud, yeah. Doing crucial repairs on bridges, pipelines, heavy equipment, construction sites. It boasts an incredibly wide range of applications: heavy structural steel, thinner gauge repairs, different metals.
And that all-position thing we keep mentioning.
That all-position capability is massive. Huge benefit for complex structures or where access is really restricted. And the equipment, as we said, remarkably portable, relatively simple compared to, say, MIG or TIG setups.
Right.
That makes it accessible, even in remote locations where dragging complex gear just isn't feasible.
Right. But there are definitely challenges, too. That high skill factor required.
Yeah.
That's probably the biggest hurdle, wouldn't you say?
I'd agree. It takes significant training, a lot of practice, good instruction to become really proficient, consistently good with MMA.
You also have to contend with high levels of generated fumes.
Yes, the flux coating generates a lot of fumes and particulate matter. Good ventilation, proper respiratory protection, those are absolutely essential for welder safety.
And managing hydrogen is a critical consideration, especially with certain types of electrodes.
Very critical. If moisture gets absorbed into the flux coating from improper storage, humid conditions, it can break down in the arc and introduce hydrogen directly into the molten weld metal.
And hydrogen in steel is bad news?
Very bad news. It can lead to delayed cracking, hydrogen-induced cracking, which is a serious defect. So electrode handling and storage procedures are vital.
And finally, you mentioned it's generally considered a low productivity process because of its operating factor.
That's right. That operating factor, sometimes called arc time or duty cycle in a broader sense, is a crucial point. It directly impacts project costs and timelines.
So for MMA, you said it's typically quite low, around 30%?
Often in that ballpark, yeah. Maybe 20–30%. What that means is, for every hour a welder is technically on the clock for an MMA welding job, only about, say, 12 to 18 minutes is actually spent depositing weld metal, arc on time.
Wow, only that much. What happens the rest of the time?
The rest of the time is spent on all those necessary but non-welding activities. Stopping to change electrodes every few minutes, chipping off that solidified slag after each pass, maybe grinding out little imperfections or preparing for the next pass, repositioning themselves, repositioning the workpiece. It all adds up.
And how does that compare to other processes?
Well, you compare that to semi-automatic processes like MIG-MAG or gas metal arc welding. There, the wire feeds continuously. There's often less slag or none. The operating factor can easily be 50%, 60%, even higher in some setups.
Double the arc time.
Easily double. And then you look at fully automated or robotic welding, where it can be upwards of 90%. The machine just keeps going.
So that fundamental characteristic, the stop-start nature of MMA, really impacts its overall productivity.
Absolutely. It makes it slower for high-volume production work. But again, that's traded off against its incredible flexibility, portability, and suitability for those unique repair or field fabrication tasks where other processes might struggle.
Right, the right tool for the right job. And even with the best welders, imperfections can still happen, right? Even for skilled hands.
Oh, definitely. No process is perfect, and MMA relies so heavily on the operator that small inconsistencies can lead to defects.
We looked at some common ones. Slag inclusions, for instance. That seems like a classic MMA issue.
It is. Often results from poor technique, maybe not cleaning the slag properly between weld passes. If you weld over trapped slag from the previous bead,
It gets stuck in there.
it gets trapped within the weld metal, creating a weak spot. Or maybe just insufficient cleaning of the joint beforehand.
Then there's porosity, little gas pockets.
Yep, porosity.
Yeah.
Looks like tiny bubbles or holes trapped in the weld. This is very often caused by damp electrodes, that moisture issue again, releasing hydrogen or water vapor into the arc.
So proper storage is key.
Crucial. Or it could be from welding over contaminants on the base metal, grease, oil, paint, rust that vaporize and get trapped.
Okay, what about lack of root fusion or penetration?
Another common one, especially in critical joints. This usually points back to incorrect settings, maybe amperage too low, travel speed too fast, or an improperly prepared joint, like the root gap being too tight. The weld simply doesn't melt deep enough to fully fuse with the root of the joint or the adjacent pass.
Weakens the core.
Fundamentally weakens it. Undercut is another frequent flyer. That groove melted into the base metal right next to the weld bead.
We mentioned that with high amperage.
Often caused by amperage being too high for the position or material, but it can also be technique incorrect electrode angle, maybe arc length too long, or travel speed issues that cause the arc force to gouge the base metal without depositing enough filler to fill it back in.
And arc strikes, those little burns outside the weld.
Yeah, those accidental little burn marks on the parent metal away from the actual weld joint. They seem minor, but they can be serious stress concentrators, especially on critical components. Usually a sign of carelessness, maybe an incorrect arc striking procedure, lack of skill, or sometimes even a poorly connected ground clamp causing the arc to initiate somewhere unexpected.
Attention to detail matters.
Hugely. And finally, hydrogen cracks. You mentioned those earlier, right? Those insidious cracks that might not even appear until hours or days after welding is complete. They're typically linked to that deadly combination. Hydrogen in the weld metal, often from damp electrodes, high residual stresses from welding, and a susceptible microstructure in the steel. Understanding these common imperfections isn't just about fault finding, it's about recognizing how critical technique, preparation, and material control are in MMA welding.
Absolutely. So wrapping this up, we've taken quite a deep dive into manual metal arc welding from its pretty humble origins back in Russia in 1888.
A long time ago.
All the way to this intricate dance of current, voltage, and travel speed that skilled welders have to master every single day.
We've really seen how the seemingly simple concept of striking an electric arc evolved into this incredibly versatile, indispensable tool, but one that remains profoundly reliant on the nuanced understanding, the precise control, and almost the intuitive feel of the human operator.
It really is a remarkable blend, isn't it? Science and artistry, maybe?
Yeah.
A testament to enduring human skill, especially in a world that's automating so rapidly.
Well put.
And that leads us to our final thought for you, our listeners.
Yeah.
Given this enduring legacy of MMA welding and its fundamental reliance on individual human skill, even as automation sweeps through so many other industries, what enduring lessons can other fields maybe take from this unique blend of precise engineering and individual craftsmanship? What stands out to you as the most surprising or perhaps the most significant aspect of MMA's continued relevance today? Lots to think about there. Thanks for joining us on this deep dive. Until next time, keep exploring.